Let's review what we've already covered about the Bohr atom. Bohr said that an electron moving in a circular orbit in the nth energy level of a hydrogen atom had an energy given by that equation in yellow, where R sub h is the Rydberg constant, and it has the value 2.18 times 10 to the negative 18th joules. From the equation, we can see that when n, which is the energy level, equals 1, then the energy of the electron is equal to negative 2.18 times 10 to the negative 18th joules, and that's because this fraction turns to 1 if n equals 1, and E sub n gets closer and closer to 0 joules as n increases. So let's do a problem where we use this equation for the Bohr atom. Let's find the wavelength, frequency, and energy of a photon of the emission line produced when an electron in a hydrogen atom makes the transition from n equals 5 to n equals 2. If the electron starts in the 5th energy level and falls to the 2nd, it's going to emit light of a particular frequency, and it'll have a particular wavelength, and it'll have a particular energy. And those are what we're asked to find. So let's start with the equation for the energy of an electron in a hydrogen atom in the nth energy level. For n equals 5, notice we put the Rydberg constant in there. We have 1 over 5 squared. That number, of course, is going to come out negative, and there's its value. We're going to use the same equation, but this time for n equals 2. I'm not going to show the work, because I trust you can do that. The only thing that would change with regard to what's shown above is what's here in the denominator. It will be 2 squared rather than 5 squared. And that result is right here, negative 5.45 times 10 to the negative 19th joules. The electron possessed this much energy when it's in the 5th energy level, and it possessed this much energy when it's in the 2nd energy level. What I'm going to do here is I'm going to change this energy that the electron had in the 5th energy level such that the exponents are the same. Notice this 10 to the negative 19th. I'm going to change this value to 10 to the negative 19th. And the way we do that is, if the exponent goes up by 1, because negative 19 is larger than negative 20, then the number out front must go down and get smaller by 1 jump of the decimal place. You can convince yourself that these two quantities here are in fact the same. So what we want to do is we want to find the difference between the energy that the electron had when it was in the 5th energy level and the energy that it has when it's in the 2nd energy level. And that difference is right here, 4.58 times 10 to the negative 19th joules. That's the difference between this number and that number right there. And that, in fact, is the energy of the photon of light that is spit out of this hydrogen atom. The change in energy of the electron is exactly equal to the energy of the photon of light that comes out. Now that we have the energy, we can use this relation to find the frequency. We've covered this relation in a previous lesson. The energy of a photon of light is equal to Planck's constant times the frequency. Planck's constant we know to be 6.63 times 10 to the negative 34th joules per hertz. We just found the energy of the photon, therefore we can calculate the frequency in hertz. And finally, the last thing we're asked to find is the wavelength of this photon. We know that the speed of all light is going to be 3 times 10 to the 8th meters per second. We've just found the frequency, so we can use the speed of light that is equal to frequency times wavelength to calculate that wavelength, 4.34 times 10 to the negative 7th meters.